Okay, so this morning we started off moving down the processing chain with pre-processing, wave separation methods, including how to accommodate non-horizontal acquisition, which can affect not only those pre-processing steps, but all of the subsequent processing steps that depend on them. We're moving this afternoon to the next set of talks on internal multiple elimination, and that fits within a method called the inverse scattering series. Okay, and the inverse. So we want to communicate what the inverse scattering series has to say in general, and why. Okay, so this is an ISS tutorial. Well, this morning we had this heterogeneous wave equation, yes, with some spatially localized source, some source signature, some c squared of r velocity. And we rewrote that equation with a reference velocity c0 and a function alpha of r, which carries the difference between the actual velocity at a position r and the reference velocity. And then we rewrote that wave equation, acoustic wave equation, in the following form. So we had a del squared plus k squared operator on the left-hand side and terms on the right-hand side that we call rho. And then we immediately found a solution for all r of that, or I shouldn't say a solution, a relationship for p for all r on the left-hand side, and an integral on the right-hand side that has two terms. One, the reference wave, which is the term further on the right here, and this is what we call the scattered wave. It's the wave that is due to the fact that the actual medium is not the reference medium. It's directly attributed to that alpha. Alpha is 0, that term is 0, okay? Okay, so what we're going to say now is, let's assume that in this equation, A of omega is 1. In other words, make it some, not only local spatially, the source, but locally temporally. And the local temporal time is chosen to be 0. Yes? That the time of the source t sub s is 0. If it isn't, it's an e to the I omega t sub s sitting there. Okay, so when you do that, the definition of a Green's function is the solution to a problem where the source is Dirac delta-like in all variables. So once you make A of omega equal to 1 here, this is now an equation not for P, but what we would call G, the Green's function for the heterogeneous medium, okay? And so that becomes equation 7 prime on the bottom, yes? Instead of being for P, it's G plus and G plus in, G plus out, and this is the reference G. And the next step is we write this in operator form. Operator form, in other words, we'll call a reference operator del squared plus k squared in this simple context, and then the actual differential operator, this is the reference operator, and then the actual L differential operator for the equations, del squared plus k squared 1 minus alpha. Then the difference between these two operators, L0 minus L, is simply k squared alpha. So then what you're seeing in this equation, this term here, is what we're going to call a perturbation, V, in a very simple context, yes? And this is, in fact, a heterogeneous media where the velocity varies and the density doesn't. It's that simple, okay? In other words, with the density and velocity both vary, there are more terms, okay? So that leads to this equation here, sort of an operator form. And that's taking us from the tutorial this morning to what is the standard way of talking about scattering theory, which is going to appear on the next slide. Scattering theory is just perturbation theory. Okay? Perturbation theory says, what's the relationship between a change in the medium and a change in the wave field? You don't want to say which came first. From the math point of view, there's not one came first, okay? We might think if you change the medium, what's the change in the wave field? It doesn't know that. It's just a relationship between the difference in a medium and a difference in the wave field, both within and outside that medium, a relationship. So to have that conversation, we're going to say, assume that the actual medium is LG, described by LG as delta. L is some differential operator for actual medium, whatever your medium is. It could be electromagnetic, it could be elastic, it could be anelastic. Whatever it is, your actual medium will have parameters in here corresponding to actual medium properties. Yes? The reference medium here, similarly, this will be the impulse response or Green's function for some reference medium for that same differential operator, and these are a differential operator governing propagation in the reference medium, and L0 has reference medium properties, and whatever model you have in mind, yes? Okay, then it's convenient, because it's perturbation theory, we're going to be looking at what's the difference between G and G0 and L and L0. What's the difference in the wave field in the two media and the difference in the properties in the two media? So the properties in the two media, difference in the properties will be characterized by this operator V, the difference between L0 and L, yes? Now, and there's a convenient also to write G minus G0 as some scattered wave, meaning it's the wave, the part of the total wave that's due to the difference in properties, okay? This equation here, this equation is an operator identity that you can think of as justified by that on the bottom, yes? With this simple acoustic thing, yes? Gave you that form, but in general, you can derive it immediately by thinking of L and G0 and all those as operators. But it's essential for this meeting to understand that identity. That identity is the same as A squared plus B squared is C squared. Pythagorean theorem, that kind of immutable within Euclidean geometry, of course. But it is, so if you were in a rush and someone said, how do you prove this? You were in a rush. Since it's so important, this operator, it has consequences. Many, many consequences, some of which are going to make us uncomfortable. Okay? I'd say just about all the consequences, including for amplitude analysis. It has a message that everything we're doing today in amplitude analysis is intrinsically and fundamentally wrong. That's what this equation says. You'll see that, okay? In other words, it has very clear messages. So to understand its basis is very important. So if you have this business LG is delta, you can think of this delta as a representation of some unit, a dyadic or something. In other words, you can think of these in some way as inverses, yes? So if you think of this guy as roughly L inverse, yes? The inverse, in other words, to get G, you invert this, yes? You invert that operator. So that would give you G is L inverse, yes? Roughly among friends. You have to be careful, left, right, inverse. I'm not getting that serious, okay? We're saying if you were forced in an elevator to prove this is what you should say, okay? Here you go. And this V, we said a minute ago, is L0 minus L, by definition, this guy. And then you have L inverse, and then you see it. This times this is 1, this is that. This times that is 1 minus, it's over. Clear? That's the operator. Or you could go back to your acoustic case that we just did, where we had G0 plus, you know, all that. Okay, so that relationship carries consequences. This is a very old relationship. It didn't start with us. Okay, so the issue here, or this is a relationship here. This is not a solution for G. A way to make this a solution to G is make a series of approximations, if you want, and say, well, here's G is G0 plus something. Let me put this thing in for the first approximation for G. That's called the Born approximation, okay, right there. The forward Born, the invert, okay? And then you can say, well, now you have another approximation, G0 plus G0 V G0, put that in for G, and keep doing that. You do that, you get this series called, by the physicists, the Born series, called the Neumann series by the mathematicians. And again, it's old, and so this is a modeling series. This is a way to generate a wave field, not normal. This, if you're looking for normal, you're in the wrong consortium, okay? If you do normal modeling, you do finite difference, finite element, lattice Boltzmann, yes? Reflectivity. You directly determine the wave field in terms of actual properties, yes? Actual, yes, all those methods. This is perturbation theory. So it's going to model, I'm not advocating this, I'm saying that what this is doing is making the actual wave anywhere in the medium, out of the medium, in terms of L. In other words, if I want G, I got to have L. But it's not doing this directly in terms of L, it's breaking L up into L0, L is L0 or something minus V or something, yes? So this has to produce G. Actual properties produces actual wave, yes? But it produces it in terms of L0 and V. How does L0? L0 enters as G0 and V enters as itself, okay? So when you're seeing this G0 thing here, you're seeing an L0, something about the reference, yes? And the V gives you the difference. But this is a tremendously profound statement. First of all, if you want to do modeling, you've got to tell me L. You got to say it's elastic, isotropic, or elastic and isotropic. You got to tell me the form of the differential operator, the model type, yes? And you have to tell me the properties within that model. I have to know everything. In other words, to know what the right-hand side is here, I have to know L. It's in two pieces, but you have to know L. If you say L, the differential operator, what differential operator? You got, yes, electromagnetic, yeah, you understand? You have to tell me what physics, what model type, and then within the model type, you got to tell me every detail of the properties, yes? Otherwise, I don't know L, yes? Is that clear? So, this series says to generate data, you have to know the medium. That's modeling. So that's one thing that scattering theory agrees with the rest of the world, okay? The forward scattering theory says to model data, you need to know the medium, okay? But it says something very profound. It says, imagine you had an L0, you had some reference medium, and you perturbed it. You changed it, I don't care how. You took one reflector and moved it an iota, or you took one point of density and changed it by 1/1,000,000%, yes? any change, if you have any change V, then the difference in the wave field, this is the original, G minus G0 is the difference. The difference in the wave field due to any change in a medium is nonlinear to that change. Nonlinear to the change. The simplest is Zopert's. Zopert says, I have a homogeneous whole space, I send a plane wave down, just goes down. Suddenly I perturb. I say it's still that homogeneous until here, and now I change it to make it a different homogeneous, yes? Suddenly you get a difference in wave field. That difference in wave field, all those reflection coefficients are nonlinear to that change, yes? You can make approximate Bortfeld and all that, but that's a very simple realization of you made a change and the difference in wave field, nonlinear, V, V squared, and so on, yes? Okay, so that's a modeling machine. We can, the scattered wave, which we call G minus G0, is some kind of, you could say order by order in V or VG0. We can call this first term here the portion of the scattered wave that's linear in V, or VG0, yes? This is the portion of the scattered wave that's quadratic in VG0, and so on, yes? What we measure, in other words, we will measure the total field in seismic. We have a phone and we measure everything it measures. But we're not interested in general in the total field. We're interested in what has come from the Earth. So you identify and use and remove the part of the wave that has not reflected because you're trying to interrogate the Earth. The part that is not reflected carries information about the nature of the source and so on, yes? Useful, but we separate it. So the idea is that this scattered wave, the difference between, let's say, we're going to assume in this entire discussion that our reference is homogeneous. And in fact, water homogeneous. G0 is going to be a propagator in water for the seismic, yes? So the G0 would just be in water, what would propagate, yes? And then maybe with a free surface if you want, yes? So D is the difference. D is the measured values of the scattered field are what we call data. Data in terms of interrogating the Earth, okay? Interested in V. So the point here, a very important point, is that this forward series is a geometric series, okay? A geometric series. That's the big missing point. We've only said it about 8 trillion times, but people in inversion have some kind of, they go into apoplexy when they see that equation 1. So, and they're married to Taylor series. Taylor series. Taylor series, so first let's explain what is going on. We're not talking about simple AR squared. We're talking about a form. This has a form. In other words, these are operators, these are integrals, yes? Complicated operators, but the form is VG0 squared. So it has a form like AR squared. So if we just humor ourselves and say for a minute that this is some kind of Taylor, some kind of geometric series, if we associate G minus G0 with S, some G minus G0, then this looks like AR squared, and so on. And if we, again, just to keep ourselves entertained, assume that R is less than 1, yes? We will have a formula like this, the first term over 1 minus the rate. Well, this formula is very interesting. Well, first of all, this, as we said, is the portion of S that's linear in R, quadratic in R, S1, S2, and so on. The sum, as we just said, can be written as AR over 1 minus R if R is absolute value less than 1. The interesting thing is this simple formula can be solved for R in terms of S. And you get this. Yes? Just solve this. 1 minus R times S is AR, yes? You want to do that? You can see it, okay. So what it says is a geometric series has an inverse geometric series. This is a forward geometric series. AR squared. You can, in high school, you learned, give me the first term A and the rate R, and I get A over 1 minus R. But you could have been given the problem where you got the sum and the first term and asked for the rate. Yes? Under certain conditions, you'll get a rate, as long as it's absolute value less than 1. You understand? So that's the inverse problem. Why? Because V is what you're looking for. And V is the, VG0 is the R. Yes? I mean, V, in other words, if you call the reference water, V gives you the difference between earth and water. Yes? So what this says is, this R here, this series here, this is R1, this is R2, this is R3. This is not an approximate, this is the portion of R that's linear in S. This is the portion of R that's quadratic in S. You're not updating some linear. This is linear. This is quadratic. What this whole thing is depending on is the fact that nonlinear one way is nonlinear the other, and it's geometric in both directions. So what we say, just like a minute ago we had R is R1, R2, R3, we imagine this VG0 like a rate. Yes? So we say, well, if the scattered wave is geometric in V, or VG0, then VG0 is a geometric series, somehow some generalized linear in the data, quadratic in the data, cubic in the data, yes? Like that. That's the point that most people in inversion in the world miss. So let me explain why. They think of Taylor series. If you think of Taylor series, everything will agree on the first term. If you think of the perturbation business as a Taylor series, meaning something like this, data of M equals data of M0 plus data prime of M0 times M minus M0 plus data prime M0, M minus M0 squared over 2, yes? Something like that. A Taylor series. Then if you get this difference in the data, they truncate this, yes? They truncate this, and you'll see they invert for M minus M0, yes? There'll be a similar thing happening here in a minute. The difference is what happens at the quadratic step. The reason it's different is the Taylor series doesn't have an inverse series. You understand? There's no, geometric has R1, R2, you understand? The difference between the change in the wave field and the change in medium properties, that relationship is a very, very special Taylor series called geometric, yes? And geometric has an inverse series. Understood? So what they do is, once you go here, what are you going to do? Take this term? So they keep updating. They change M0. They keep at the linear term, updating. And that has a bunch of issues that we'll discuss, practical and otherwise. One is the update. I'm going in the wrong direction. We'll come back to that point. What happened to that pointer? Did I put it in my pocket? over there. I need the inverse scattering series to find the pointer.
Is it in the tray?
Ah, probably, yes, thank you. Corey, you're a good man, but we knew that before. Thanks. I need the inverse scattering series to find my car. That would be useful. So, there's a forward series and an inverse series. The question is, what's V1, what's V2, and so on, yes? Okay, we said this already. Okay, this is making some point. I'm not sure it's in the right place in the talk, but there's a misunderstanding among a lot of people who do inversion that, and we'll try to clarify it here and we'll make it clear when we talk about the elastic equation. That's take a forward problem and solve a forward problem in an inverse sense, that's the same as solving an inverse problem directly. I'll repeat that. There's a confusion, okay? And Stolt and I have published papers which represent that confusion, okay? So no one's out of this. This is we, okay, have been confused on this, and I'll explain exactly the pitfall. The 1985 paper that Stolt and I wrote is confused on this subject. But that's what we knew then, you know? The point is this. The only time, so I'm saying if you have a forward problem and I try to solve the forward problem in an inverse sense, that's not the same as solving, in general, solving an inverse problem directly, okay? Let me make that clear here, or try to. Here's a forward problem, right? And here's a direct inverse, you see? This is a forward problem, a geometry. I'm going to illustrate it with this, yes? This is a forward problem. You give me A and R, I give you S. You give me S and A, I give you R. Yes? How many R's? 1. You give me S and A, as long as S over A is less than 1, you get 1 R. The only time what I just said is not true is if the direct inverse is linear. And there are times when the exact direct inverse is linear. Migration is a linear operation, is a direct inverse which is linear. It assumes you have the velocity, yes? But once you have the velocity, the data and the migration are linearly related. Yes, you do sums over the data. You don't multiply data, yes? It's linear. So if you have a relationship which is accurate like this, then solving the inverse directly here would just be R is S over A. And that's exactly the same as if I took this forward and said solve for R. You get S over A. That's why migration and modeling run backwards are so related and correct. You understand? There's not, because it's a linear direct inverse, yes? Given a velocity, you predict the source and receiver at depth. Those are linear operations. Coincident time equals 0, yes? That is a direct way to determine structure, yes? So, however, watch what happens here if it's nonlinear, yes? If you have a nonlinear, let's just take the first nonlinear. Let's just say, instead of S equals AR, you had S equals AR plus AR squared. Just that was the problem, yes? That was, you got 2 roots. The forward, right, you give me R, I get S. I give you S and A, I get 2 R's, not 1. I make it AR, you understand? Solve this forward in an inverse sense. You're solving the quadratic equation. You understand? You make it AR cubed, you get 3 roots. You get AR to the n, you get n roots. You get AR to the infinity, you get infinite roots, solving a forward in an inverse sense. The direct inverse of this is R equals S over A, 1 plus S over A, one number. You understand? Okay, so that is an important, and we'll watch what happens when we get into the elastic. what happens there, okay? Anyway, I think that's an important point. What is the problem that Stolt and I did? We write DPP, PP data, changes in lambda, mu, and rho, and we are inverting. Well, DPP is, you'll see in a slide or two, is inadequate data. That operator, G is G0 plus G0, V, G, says DPP is inadequate. It's inadequate if I said I'm going to take one trace, one function at a time, and solve for 35 parameters. Okay? We know not to do that now. So at least some people do. They'll take a generalized inverse, make it. But well, how do you know it's inadequate data? That's what we'll see. Yes? So the message from this moment, right at this moment, is if I have a formula for DPP, P data, yes? The data, and it's involved in changes of this, that, and the other, that's a forward problem, which is absolutely fine. But be careful if you're going to solve that forward in an inverse sense. To claim that that's a direct inverse is a mistake. The direct inverse for lambda, mu, and rho needs all the data components, or you're violating G equals G0 plus G0 VG. That's simple. That's what we'll show. So if that business that we just showed over here, deriving that thing, means anything to you, yes, in the elastic case, you'll see what it communicates. It tells you this is the data you need, and this is what you have to do to it. Understood? And in addition, it only asks for primaries. The direct inverse only asks for primaries. How do you know? There's an inverse scattering series. It lets you remove internal, free surface, internal. If it needed those things, it wouldn't let you remove it. You don't make the inverse scattering series do things. You understand? If it needed it for some reason, it wouldn't let you remove them. When you get to doing depth imaging and nonlinear AVO, it assumes these other tasks have been achieved. Okay. So, is there anyone here who remains not upset? Okay. Well, these are messages that I think are worth communicating. So there are people who say Weglein's against FWI. Nothing could be further from the truth. I'm not against FWI, I'm not against RTM, I'm not against compressive data, These are all methods. They're just in a toolbox and they have use. I'm not against statistics. Statistics are not the issue. Statisticians can be the issue, if you get my meaning. Okay? In other words, it's people who oversell, including ISS. ISS is not the answer to the world's problems. You're not going to have peace in the Middle East from the ISS, okay? You understand? There are a lot of issues. There are a lot of things that have to be done, as our colleagues this morning said. Look at all the conditions that have to be met. It's not condition-free, yes? And we're not against methods here. We're against people who overstate what a method is, yes? So we have to be careful, as you'll see, today and tomorrow, what the ISS is not able to yet do, yes? Okay, so anyway, if that doesn't get me in trouble, I don't know what will, okay? That statement about statistics and statisticians is not new to me. I'm sure you've heard that before. Okay. So, for example, if someone says, as we've heard more than once, the method that I am pursuing is the ultimate of method to get information about the Earth. There will never be a more capable method. Someone got up at the last SEG and said that. I couldn't believe it, okay? That doesn't have any place in science, okay? That's in a different kind of business. You'll make a lot more money, but not science. It's always a work in progress, okay? Always. Yeah. If it's the last word, then stop doing research. Anyway, got off a bit. So let's continue. So this, just like this is R1, R2, and so on, there's a set of equations that give you V1, V2, V3. Let's understand what V1, V2, what is V again? You have an operator L0, you have an operator L. L0 represents propagation of water. L represents propagation in the real world. V represents the difference in properties, right? Difference in differential operators. V1 is the portion of V that's linear in the data. V2 is the portion of V that's quadratic in the data. What you do, how do you get these equations? This might be the most important slide, this lower here. If you understand this slide, yes, there's something that will arrive to you, okay? Let me erase this. I'll try to make this fast. If you take the forward series, in other words, how do you get those equations on the bottom quickly? Because it's essential. The message from those equations is the most resist message we've ever tried to communicate. You have a forward series. Data equals G0 V G0 plus G0 V G0 V G0 and so on. And you have this inverse, V equals V1 plus V2 plus V3 and so on. The question is, what are these? How do you compute them? If you substitute this form into the forward series, every time you see V, write V1 plus V2, V1 plus V2 plus V3, and so on, everywhere, and then set terms equal order in the data equal, you get those equations. In other words, this one will have V1 plus V2 and so on, V1 plus V2. This is linear in the data. Data is linear in itself. So on the left-hand side, the term that's linear in the data is D. On the right-hand side, there's only one term, G0, V1, G0. Why should terms equal order in the data be equal? We can prove it, but I don't want to do it now. Happy to do it if anyone's interested, okay? That is rigorous proof that terms equal in the data should be equal. What about quadratic? What's quadratic in the data on the left-hand side? Nothing. It's just linear. So the quadratic contribution, in other words, D is D plus 0D squared plus 0D cubed, right? On the right-hand side, it's G0, V2, G0 plus G0, V1, G0, V1, G0. And then 0 for cubic. I'm not going to write all. You get V1, V2, V2, V1, 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 V1. These are all cubic in the data, cubic in the data, cubic in the data, cubic in the data. So you've cubic in the data on the left is 0. So what does it communicate? The first equation says you take your measurements, data, and you invert this operator G0, water speed propagation. That's analytic. That's called Fourier water speed migration, and you get V1. There's an analytic form to get V1 in terms of data. That V1 depends on data and water. V2. V2 has this guy sitting here. This guy is water. This guy, to get V1, we just said to get V1 I need, it's in terms of data and water. Water, data, water, water, data, water, water. And this, the inverse, is exactly the same as inverting this. Analytic. Okay? So you have a direct analytic for V1, V2, V3, where what happens is you have multiplicative data, data times data. This is data with G0 inverses, yes? So when you look at free surface multiple removal from Cavallo, data times data. You look at Araujo, internal multiple, data, data, data. You look at elimination, data, 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 data. more multiplies. If you got more ambition, more things to do, the same with imaging. You want to do depth imaging without the velocity? You got to multiply the image, the water speed image by itself. So what this is, it has lots of advantages. The advantages are the data is never inverted. In other words, when you do this business with iterative linear, you take L0, G0, and you get a V1. This equation right here is exactly the equation you would get if you did iterative linear. You would just call it G, D of M minus D of M0 is D prime M0 delta M, yes? This is the data, actual data in the reference, yes? That's what we call data, G minus G0, yes? And so this G0 is, this G0, in fact, is an analytic Frechet derivative at one reference. When you do this in practice, you have to have a D of M0 plus epsilon delta M, right? Minus D of M0, you understand? A nearby. But more importantly, what happens here is when they solve for delta M, since they don't understand as a geometric series, they update. They take the delta M, and they take the L0, and they take this V1 that's found here, or they will call it here delta M. This is the V1 in that language. And they'll get a new L0 prime. How did they get this? They get it by inverting this. Yes? And so that delta M already, and then the next step is they're inverting an operator that has data in it. You understand? That's the issue. Here you have an analytic inverse at every step. In other words, V1, V2, the operator that gets inverted never changes. It's just multiple. So what's the message? Well, so why don't you just find the Earth, someone would say. What are you doing all this multiple? Why don't you just go find V? Yes? The problem is this series, V1, V2, V3, taken all together, does not have good convergence properties. Does not. That was tested by Carvalho, Mattson. It has a very limited range. Even with full bandwidth, noise-free data I'm talking about. Forget about those issues, yes? It has a very small range of convergence, 4V. So that was not a good day when that arrived, that news, okay? So the question was, it's multidimensional and it's the only direct method. Are there other things that we could achieve that are within this machine? In other words, imagine that in comes data and out comes the Earth. And that things have to happen. Multiples get removed, yes? Free surface, internal, depth imaging. Perhaps that activity, yes, which is in here, will have subseries which are better behaved, yes? The free surface multiple, as you'll see in a minute, works one temporal frequency at a time. You have 12 hertz. It looks for data at 12 hertz. There's no inverse, you understand? It's just data times data at 12 hertz. Out comes free surface multiple at 12 hertz. So the properties of these subseries are very different than the whole series. In addition, there are the most of the terms in this series are doing coupled tasks. Free surface and internal, and depth imaging, and you understand? Trying to do everything it can, order by order. Those are the terms that cause the lack of convergence. Because every subseries that we've used, which is isolated task, only free surface, only internal, only depth imaging, has never had a convergence problem. Yes? There are terms we're avoiding, yes, that have that issue. Okay, so the point is this. If you imagine that there's a machine that inputs data and outputs the Earth, and they have these tasks within them, whatever this machine is doing, you take pieces of it. Every term here, every piece of a term is in terms of water and data. So if I get a subseries Carvalho's subseries for free surface multiple removal, it eliminates free surface multiples in terms of data and water. Internal the same, yes? Depth imaging the same, yes? Because this whole machine, there's not a term in it that's not involved G0 and data. So whatever pieces you pick have that property. So that communicates that every task, Q compensation without Q. You'll see an example. There's a subseries that does Q compensation without needing to know or determining Q. That's in Lira's work when they were here, you know? That's amazing. It's mind-boggling. You take a data that's gone to absorption, yes? You put it in a certain specific subseries, and out comes a data that never had absorption. And it doesn't know the mechanism. That last part boggles my mind, okay? I don't care. There are things about this series that just, it's smarter than, okay, well, you'll see how smart it is when we start, okay. Anyway, that's the message. The message is every task that you can imagine seismically is achievable. That communicates directly in terms of data and G0. That's simple. The job is go find out where it is. That's not simple. The internal took 8 years. Took a while, okay? Knowing it's there and finding it, not the same thing, yes? You can prove easily that there are more irrational numbers than rational, yes? Uncountable. Go prove square root of 2 is irrational. There's no direct proof. You know, to actually point at one, you get the analog. Okay, so this set of equations, okay, so it's a blow up here. We'll get, there's two interesting things here. Let's say you had, there's two kinds of nonlinearity that the inverse series is dealing with, and they deal with them very differently. If you haven't heard this before, you might find this interesting. There are two kinds of nonlinearity. One is innate, and one is circumstantial. What I mean by innate is, to have an inverse problem, there's something I have to have that I don't know. Yes? In other words, if I know everything in the world, I don't have an inverse problem. Yes? So the simplest thing to assume is you know and then you don't know. Yes? Something you don't know. As long as there's something you don't know, a V, that is innate. Meaning the only way you get rid of that is to know everything. Yes? There are other nonlinearities that are circumstantial. For example, locate this reflector. You give me the velocity, it's linear. You don't give me the velocity, it's nonlinear. But I don't have to give you all the information about the whole world. I just have to know enough to get to this point. So it's circumstantial. Depends on your information, but not everywhere needed to get rid of that nonlinearity. Yes? So circumstantial nonlinearity have a very interesting property. All circumstantial nonlinearity, this is something none of us dreamt. For any circumstantial nonlinearity that the inverse series is dealing with, it decides, given your data and its purpose, whether its purpose is called for. You'll see that. In other words, let's say you're trying to do inverse scattering depth imaging, yes? And you don't want to assume you have the velocity. Well, let's say you by accident had the velocity, or had it somewhere and didn't have it somewhere else. It will decide, and you'll see examples, yes, where it decides you don't have an issue here. It just stops. It says, oh, you don't have an issue here, and here you do. And then you start to help, and it says, you still have an issue. You didn't help me enough. It decides with your data whether its purpose is called for and whether you still haven't done enough. That's amazing to me, okay? That's absolutely, for example, if you give me a primary only and you put it in the internal multiple algorithm, you'll get 0. The second integral will be, it says you don't have an internal multiple. What are you aggravating yourself? Okay? In other words, it determines for anything circumstantial whether the issue that that algorithm deals with is called for in your data. Now, there's an exception, of course. Free surface multiple, and you'll see an example. Anything below the cable, the inverse scattering series, it's going to have its own attitude, its own opinion about what you say. You say this, it says not, or yes, you know? Above the cable, it can't argue. If it assumes you got your act together. If you say there's a free surface, it says okay. Okay? So if you give it a primary, it assumes there's also going to be a free surface multiple coming. Yes? But in turn, you understand? Anything that has to do with below, it has opinions about what you say and where you say things are needed. So that's an interesting thing about circumstantial. Okay? Any circumstantial nonlinearity that the inverse scattering series deals with will determine for your data whether those terms dealing with circumstantial nonlinearity are called for or not. And it doesn't wander around. What a nightmare for me, and you probably, in early meetings of this consortium, you probably remember when we first got involved with the ISS imaging, I was worried that it's C0, and it really is C0, okay? But it's perturbation theory. It lives to perturb, you know? What else up here? V1, V2, so it will make it deeper, make it shallower, make it deeper, make it shallower, and 8 billion terms later, tell me you were right, sorry. You know, your computer melted, but you were right, you know? That was a nightmare, you understand? It's perturbation theory. It doesn't do that. If it determines your velocity, and you'll see how it does that, yes? Your velocity is appropriate for that data. The first term after conventional migration is in the integrand 0. Okay? You don't integrate. The integrand says stop. Okay? That's what purposeful perturbation is. How in the world it does it, I don't know. We watch it. I guarantee you we just capture these terms and say, oh, you see how it's doing it? We don't make the algorithm. We extract it and then say, isn't that amazing? You understand? I couldn't imagine how to figure out how to get data in an algorithm to say yes, it's right, or yes, it's wrong. Yes? But it knows. You know why? It's one word that makes that purposeful. It's the word direct. The word direct should not be underestimated. Direct means every term in that series has got a purpose. It's not just moving, it's not perturbation, it's purposeful perturbation towards a goal. Some objective it's trying to achieve, specific. Interesting, yes? So if I seem to be on some kind of mission of direct, that's why. I'm in awe, you know, of what that leads to. I guarantee you, Stolt and I had no way of dreaming that this thing would ever be that smart. We thought it was a series and worry about the dots. We didn't want the series. Who wants a dot? How, you know? The thing was the dot was its whole strength. If we had a closed form, it's either everything or nothing, and it's probably going to be nothing. With the dots, you got all the working parts. You understand? The machinery is open, so you take this, oh, you're doing this, you're doing that. If it's closed, you understand? It's like a watch you can't see inside, yes? So the dots we were trying to avoid for several years, that's the whole benefit. Yes, the fact that it's all spread out. Yes, the activity is there. Okay, I'm sure this was no part of my prepared talk, but there's never been a prepared talk. Okay. There you go. Only if it decides that it has an issue, it computes. Okay, so these are tasks: free surface multiple removal, internal multiple, attenuation, elimination, Q compensation without Q. These are things that people in seismic processing would like to achieve. The message is all of these things should be achievable directly in terms of data without subsurface information. So here's the elastic. Okay? We made some comment about elastic. Here's a simple 2D heterogeneous elastic equation. Yes? Just to illustrate, we're looking at this thing. Nonlinear parameter estimation. If you're looking at nonlinear parameter, you have to tell me parameters. You got to settle. free surface multiple, internal multiple are model type independent. Not only don't care about the subsurface, you'll see, they don't care what earth model type you have. That again is mind-boggling, yes? You'll see that Jingwu will show you an example with anelastic, yes? Inelastic, doesn't care. So, but a nonlinear parameter estimation cares about what parameters. You say find the parameters, it says which parameters. You say well, it's model type independent parameter, you know. It says you're crazy, you've gone off the deep end, you know. You got to have parameters in mind for it to look for. You understand? That's the only task that we're convinced must be model type dependent, yes? Understood? Okay. So we're going to put in this G equals G0 plus G0 VG. That's all we know, that identity. So here's an L. This is some differential operator. This is a P and S waves. This is a force that's only a P, a force that's only an S. And this is the V. We're assuming it's PS in a homogeneous isotropic medium. The L0 is, there's no off diagonal, yes? So the L0, PP, L0, they're just acoustic looking things in a homogeneous medium in the PS world. So the point is this. Here's your forward. Data. What's the point? Where did this thing come from? That's the key. This elastic thing is a matrix. In other words, P and S are coupled. Yes? You have a matrix. For homogeneous, not. P is alone, S is alone, isotropic. But once it's heterogeneous, you have a matrix relationship. Yes? So this operator is a matrix, V is a matrix, the data is a matrix. V, you know, V squared, you understand? If you just write the elastic 2D heterogeneous isotropic equation, this is what follows, okay? For that L and that L0. That's not arguable, okay? And then there's VPPs, V1 PP, V2 PP. What do you mean V1? V1 is the portion of the part of VPP that's linear in the data. What data? That data matrix. That was the data, okay? So watch how we can get off track. Here's all the VPP in terms of VPP changes in lambda mu rho and so on, yes? VSS only in terms of mu and rho, yes? The normal kinds of things that those perturbation operators. So let's look at the inverse. The inverse says data G0, V1, G0, yes? The second says G0, V2, G0, G0, V1, G0, V1, G0, yes? Like that. The first equation looks normal. The first equation, this equation will say dpp is G0p, these are diagonal, the outer ones. So you just get a simple equation. This is where Stolt and I went off track, because we didn't look at, we looked at the first term and thought that first guy up there says dpp is G0p, V1pp, G0p. And this guy has linear estimates of changes in lambda mu rho, because it's a 1, yes? So you would think, oh, I want to get, so I get the linear estimate, you might think, of lambda mu rho just from dpp. Nothing wrong with that thinking. Until you say, well, how are you going to get V2pp? Yes? If you think you're going to get V2pp by using this again, that's where you went off track. Because look at V2. Here's the second equation. This V2 G0, you know, it's the same G0P, V2PP, G0P. If you look at what this says here, there are, that's what V2PP is. Whoop. V2PP cares about V1PP. Oh, what's going on here? It's a conspiracy. V1PP and V1PS and V1SP. Suddenly the second order in V1PP, the second order in VPP cares about other data components. Okay, you understand? And when you look at G0PP, V3PP, it not only cares about PS, it cares about SS. Yes? So what the message is here is the inverse scattering series, if you're looking for changes in lambda, mu, and rho, and nonlinear, you have to understand that you're inverting that operator. And so the inverse scattering series tells you, first, the data you need to do direct inverse. V1, V2, V3 are all linear in that data matrix. And in addition, it tells you exactly what to do to that data. Okay? What to do to the data to get the second order. This is not an update of linear. This is you do this and you get V2. Yes? You follow? There's no updated background. Yes? It's all in terms of G0. Yes? Okay, so that's the message. The forward is geometric in VP. The V operator, the inverse is geometric in the data operator. It's that simple. If you did what Stolt and I did, which is invert DPP, and only stay with that, you violated that operator identity. You stay linear, okay. You start thinking of that more seriously than that, where you start matching and so on, yes? With that data, you're matching the wrong data. And this says you don't match at all. You just find the linear, find the quadratic, find the cubic. Don't match, don't search. Those are formulas for the linear quadratic component of changes in elastic properties. Yes? Formulas. Okay. Okay. So this is saying that it's not iterative linear. So this is saying what we made violates G equals G0 plus G0 VG. If you're staying with that equation, this is Q compensation without Q. The top is the data. This is Christenen and Jose Eduardo Lira when they were here. The upper was data that went through absorption dispersion. The bottom is the data that's recovered from it. Yes? There's a subseries that does Q compensation without Q. Okay? Interesting. And it looks very much like the ISS depth imaging, because Q doesn't occur at boundaries. It occurs over duration. The whole layer does it. And depth imaging is not just the wrong velocity. It wants to know how big is that layer that you got the wrong velocity. Yes? Duration comes in. And the algorithm that does this is, I'd say, identical, except for the meaning to the ISS depth imaging. Okay. Let's race through this. Free surface and internal multiples. This is a derivation of the free surface algorithm. Let me race through this very quickly for those of you who haven't seen it. This is a cartoon of, if here's a data without a free surface, here's a data with a free surface. Some kind of unit pulse comes down. Here, no free surface, so this pulse enters the Earth, and out comes a train, R of t, that has primaries and internal multiples. Yes? There's no ghosts, there's no free surface multiples. This, you have one goes down, and RF comes up. This RF is the total up wave. In this example here, we are assuming deghosting. You can see how important. What does that mean? we are assuming that the source sent a wave down and that this measured a wave going up. That's deghosting. This is what happens, yes? And this is what happens, yes? So this derivation of the multiple free surface multiple removal has assumed deghosting. So all of that you saw this morning, if that doesn't happen, this derivation's gone, yes? You understand? It won't work. So let's look at this. We'll call this 1 and call the total upwave that this experiences here with the free surface R sub f of t, and the Fourier transform is R. What we're going to do is we're going to make this data from this, and that will allow us to then make that from this. If we can turn this into that, we've removed the free surface. This is the total upwave, meaning it's a primary, an internal multiple, a free surface multiple, yes? All of that is this. No ghosts, yes? The total upwave in the presence of a free surface. So, okay. So here's how it works. One goes down, this unit pulse, one goes down, and out from the Earth comes this train R of t, R of omega in the frequency domain. That train that exits the subsurface consists of primaries and internal multiples, yes? Down, out comes a train of events. That train of events heads north, hits the free surface, picks up a -1, and goes south. A huge train of, like a wavelet, exactly like a wavelet. So this, you understand, this is R of t. This is the guy that would have been there without a free surface. But it heads north, hits this with a -1, and heads south. This heads south, and this -1 from this free surface, the pressure wave, this is like a wavelet. In other words, the convolutional model says if one enters, if one goes down and produces R of omega, then if this goes down, it produces this times this come up. Yes? If one produces R, then A of omega down produces A of omega times R of omega up. Yes? Yes? The convolutional model. That's where this came from. So this goes up, hits again and comes down with R squared. Add up all the up waves. You get this, Y up waves. We're talking about deghosted data, yes? This wave is down, yes? So if you add this up, R minus R squared plus R cubed, you get that R sub f of omega is this form right here, yes? In other words, R of omega minus R omega squared plus R cubed is this, yes? In other words, it's a geometric, and then you can solve for R of omega in terms of RF, and you can expand it like this. This is the free surface multiple algorithm. You take in data, deghosted data, no direct wave and all ghosts removed, and you take the data and you multiply the data by itself, and you multiply the data by itself again, yes? And what did you assume in this derivation? Two things: that there's a free surface with a -1 and a convolutional model. That's it. You don't know where the water bottom is. Yes, you don't know how many layers there are. You don't know if it's acoustic, elastic, anelastic, anisotropic. You don't know and you don't care. The algorithm doesn't care. That's a model type independent formula. Yes? No information about the subsurface whatsoever. Yes? So that's an example, but look at multiplicative. What happens here? This is data. This is your primaries, internal multiples, and free surface multiples, all in this. When you add this to this, two things happen. every multiple that's hit the free surface once is eliminated, and all higher order free surface multiples are altered. And they're altered in a way that when you add this to this to this, first and second order are eliminated. So it's complicated. It isn't just this plus this removes first order, yes, but every other higher order multiple gets prepped so that the next term arrives, it can eliminate. It's interesting, you know? This is a non-trivial story, and this is 1D normal incidence. So what this shows you is, let's make a data where the multiple is invisible, yes? Here's a primary, here's a free surface multiple, here's a deeper primary. You can make these two cancel, yes? Cancel. You put these three, you put these three events. This is the first primary, the second primary, and the free surface multiple. Yes? Here, you put this in the algorithm. In other words, these two cancel. The only data you see is this. You make these cancel. So your data is just R1 delta T minus T1. You take RF of omega, which is this, from here, you square it, you get R1 squared e to the 2i omega T1, add it to this, and guess what? You got two primaries. It recovers the primary. Why? It says, you told it there was a free surface multiple. If it sees this, it knows there's got to be a free surface multiple. So it predicts the negative of it. You understand? And the negative is exactly the primary that it canceled. Yes? So it recovers that hidden primary. This is the grown-up version of that RF squared. This is Carvalho's free surface multiple removal. D prime means it's deghosted. Yes? Okay, deghosted. And this is that algorithm. This is the internal multiple, Araujo et al. This is a water speed image. Whoop. Data, data, data. It's cubic in the data. The beginning of internal multiple takes a higher order term than free surface. Why? It doesn't know where the down reflection is. It has to work harder. Yes? So cubic is where okay. This algorithm predicts the precise time and approximate amplitude of every first order internal multiple and requires no subsurface information. Those last words are what separated it from everything. Requires no subsurface information. Okay? This is that list of people that use it. Okay, so this talk is over now. I know you thought it would never end. I thought it would never end, okay? This is being taped. I'd like to thank Andrea for doing this. It's taped and with sync slides. In several weeks you can get a link to it, and it's useful if you suffer from insomnia. You can put it on. I use it. It works. And but you can select anything you want because there's a whole menu, thanks to Andrea. Okay, so here's the point. The internal multiple, as we said earlier today, has this property. It doesn't require subsurface information. Nothing from the ISS requires subsurface information. So it's not news, you know. It would be news if it did. That thing says D and G0, go find whatever you're looking for, yes? So, but it is a term. No one says that when you find a term that you've done what you want. It has done part of what you want. It has predicted the precise time and approximate amplitude of the internal, and as we say in practice, people use energy minimization, adaptive subtraction, assuming that the energy will be less for an isolated internal multiple if that multiple wasn't there. So that is a very useful tool. It is the most capable current capability in industry for dealing with internal multiples. It absolutely fails when you have primaries and internal multiples that interfere. Fails, okay? You're better off not doing that. People do it, they do it very gingerly, you know, because they're worried about that primary. And so they probably didn't get the multiple out is the issue, but they rather keep some multiple in than damage the primary. That's the worst thing you can do, yes? So the response that we're proposing to that is prerequisites for onshore. Onshore, there are many, many cases where you have interfering primaries and multiples. And the pre-processing steps are challenging onshore. And you saw Jingwu, Zhen Zhang, and Yuchang Shen this morning talking about pre-processing, onshore, offshore, different. So that's crucial. That has to happen. And then we need beyond attenuate, yes? And then, last but not least, we need a new adaptive subtraction criteria. And I'll give an example today for the free surface. A criteria that derives from the algorithm, a property of the algorithm that you're driving. In other words, you need a dial that recognizes that I don't care what these equations are, the world is more complicated, yes? So you need some way to accommodate. That's what the adaptive is, an adjustment, yes? A dial. Make that dial, though, work aligned to the algorithm rather than come in separately, yes? Make it always be supporting a property of the algorithm, is a way of saying, yes? So that was, we have a candidate for the free surface. We're going to be looking for one for the internal. Why? Because to think that these two on field data are going to do the elimination is some form of arrogance. I don't care. You understand? We're talking about you need an adjustment, yes? Adjustment, the cable, the right? The acquisition, yes? The sampling, on and on, noise. Okay, so with that too long talk, I'll introduce my colleagues, Yang-Li Zhou and Dr. Chao Ma, who are going to talk about this second item, internal multiple elimination, okay? Do you need a break? Probably need after that talk a permanent break, right? Okay, lock the door, make sure all the sponsors are paid before they leave, okay? Oh, speaking of which, Zen, yes, Zhen Zhang here has memory sticks of the annual report because there's a huge activity here and we're just giving you a sampling. So you can take that and look at reports that sort of follow this, yes, in more detail.